All right, we are back for more. So we were talking a little bit about the nitration there last time and the reduction, and then we talked about the alkylation and we worked our way through that. All right, we talked about some other ways of doing the alkylations by generating cations from non-halide alkyl halide sources. Right, we talked about some of these superacids there and what we can do, and just kind of continue along those trends. Um, Lastly, we talked about these blocking groups here, and I just wanted to maybe, let's say, clarify something here also. If we are here, we can also get rid of the blocking group by basically just heating this up. So we can get rid of this by just heating this up also. Well, I don't know, maybe not clarification there, but just so you guys are aware. This kind of goes back to what I was talking about earlier there. It's pretty easy to get rid of that sulfate group, surprisingly. We can even put this in, well, anyway, I don't need to get into too much detail with this. The point being, these blocking groups, we can put them under dilute sulfuric acid or just heat this up. And again, this is one of those themes for the semester being, in some cases we don't want to add more acid around, and just keeping an eye on what we want to do with the rest of our functional groups. Okay. Anyway, all right. Who cares, right? Moving on. So, what I did want to talk about is going back to the idea of the alkylation, right? So remember, one of the limitations with the alkylation is that we do generate that cation, and then it can rearrange, and we can do all this stuff. Or excuse me, we can't do all this stuff. Whenever we generate that cation, we have to pay attention to all that stuff that can happen there, right? So what we want to do then is, how can we generate a cation and not have it rearrange? Well, I mean, we could talk about maybe, generating a tertiary cation, and that's fine, but that limits us in some ways, right? Because we have to be able to start with a tertiary cation and then, do the work from there. So what we can do then instead is acylation. And so let's talk about Friedel-Crafts acylation. Well, first of all, what is an acyl group? An acyl group is essentially this. Right? Well, okay. Change colors here for a second. Let's do this here, right? An acyl group is essentially a carbonyl group, okay? Now, we've already kind of known about this when we talked about acyl halides, right? So something like acyl chloride, where we would have generically this guy right here, right? And we talked about these quite a bit. They're our very reactive carbonyl species. We can generate them using thionyl chloride from the carboxylic acids, blah, 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 right? We talked a lot about that. Please go back and, review your notes in the carbonyl chapter about these, because this is what we're going to end up using, okay? We're going to end up using these acyl halides to add those groups to our rings, okay? We will still generate a cation along the way. Okay, when we use these acyl halides, we will still generate a cation along the way, but, boom, boom, boom. Okay, so let's get this set up here real quick. Here is the generic reaction. Okay, this. Let's just keep it simple. All right, we'll start with an acyl halide, our benzene ring, and our Lewis acid catalyst. And at the end of the day, we will end up with that. So we're adding our acyl group to our ring. Now, it shouldn't be too shocking, I guess, that the mechanism for this is going to be very similar, okay? So we've always been talking about our three-part mechanism there, right? Let's generate our cation. You guys can probably do this, before I'm even finished with it. Oops, let's make this a little bit nicer looking. That looks great. Boom, 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 boom. Right, here we go. So as our intermediate, we have this. right? And so the same thing that we talked about last time when we were talking about these mechanisms, right? This bond here in blue, right? That's going to be weak, and it's pretty much going to break off there, right? We are going to generate that cation in this case, which leaves us with this, right? And our good old buddy AlCl4, right? So I'm just going to, I'll skip drawing that out. So here, right, this is our generation of our electrophile, right? There's our good old buddy, Mr. Electrophile, right there. Now, wait a minute, you might be saying, right, for those of you guys who are observant and looking at this and thinking along, right, you see that this is a primary carbocation, and, you know, what do we know about primary carbocations? Well, we don't want to form them, right? So, what's going on in this case, right? Well, it's a cation, but, right? Is this any normal cation? Well, right, I think you guys might see where this is going, okay? We can stabilize this. I'm going to draw this a little bit weird looking here. Right, the geometry here is going to be a little bit different looking, okay? So we can resonance stabilize our electrophile. Yeah. Okay, our electrophile here, okay? Cool. So this stops this from rearranging, okay? This stops this from rearranging, and that's exactly what we wanted, okay? Now we don't have to worry about rearrangements, but we still do have to generate an electrophile, right? So we do still have a cation. They're still going to behave as a cation, right? But this is a resonance stabilized one. So we're not going to see any rearrangements, which is great, okay? So let's finish up this mechanism then, right? Here we have our benzene ring. Boom, 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 boom. Let's bring in Mr. Cation here. I'm going to have it face this way. Okay. Hopefully you guys can take care of it from this point, right? Nothing different so far. This is in black, excuse me. Okay. Here we go. There's this. Generate that. Reform our ring. The aluminum, right? This guy's going to come back, right? And that's going to hit that and fall down and reform our pi bonds. Whoops, that didn't look too nice. Green, green. This is black. This will be black. And this will be in green here. Fantastic. Right, we also generate the HCl, and we regenerate the AlCl3 along the way. So, really, nothing different in this mechanism here, right? It's all kind of the same that we've been seeing all along, right? Well, geez, Dr. H, you guys might be saying, well, why do you keep showing us the same thing over and over and over again? Well, right, I think you guys get the point, right? The mechanism in this case isn't really going to be any different, right? We have to generate some kind of positive. It's going to get attacked by the ring. We reform the ring, right? I think I've said that a billion times at this point. Fine. Let's talk about something a little bit different then. Let's introduce another topic here, okay? So let's take the product we just made there, right? Let's take that guy. And let's do something with it. Let's, you know what, let's add a nitro group to this. So H2SO4 and HNO3, okay? Now, let me pause you guys here, right? Let's pause you guys here and say, okay, see if you guys can figure out what the product's going to be, okay? So if you guys want to take a quick pause here, see if you guys can come up with the product, draw the mechanism along the way. That's good practice, right? Green sounds good. That's going to be my product. Okay. Well, you know what? Let's do a little bit of practice here. Now, if I take this guy here instead, and I do this, can you guys go ahead and predict what the product there is going to be? Okay, that's one of our reductions, right? We're going to be getting rid of our carbonyl there. And then if I come in and my nitration, now my product is this. All right. So, a couple of quick comments. Okay. There's two things that are going to be going on here to explain this, and the two ideas or concepts are going to be the same ones that we always run into. It's either going to be sterics or it's going to be electronics. Okay. Now, we're going to have to take quite a bit of time to explain what's going on here. Obviously, it's in the book, and I've already posted a secondary link to another video explaining all this, but this is going to be a key concept, right? So what we've been doing so far have just been adding a single functional group to a ring itself, okay? Once we're done introducing, we have one more reaction mechanism that I want to teach you guys. Once I'm done teaching you guys that mechanism, then we're going to have to come back and say, okay, well, what happens as we add multiple groups to a ring? So we're going to come back and talk about activators and deactivators and orthopara and meta-directors, okay? So, something to look forward to in future videos, right? Okay, but anyway, that all aside, the last thing I want to talk to you guys here was about this, in this section at least, was about this acylation. So we can add acyl halides to our ring. We use the same mechanism. We stabilize the cation so we don't have to worry about rearrangements and shifts. And in all honesty, this is usually a better choice for doing our alkylation, just because we don't have to worry about any of those side groups in there. But it does run into this problem here, right? Running through acylation, right, runs into the problem where we will start to see different products get formed afterwards, right, if we take the next step, so to speak, okay? So we just have to keep an eye on that, and we'll come back and we'll talk about this in just a minute, right? But at least for this video, here is the idea with acylations, and that'll be it for this one. Nice short video. All right.